So what we see here is a whole bunch of angles. The red ones are angles in standard position because they start in a positive x-axis. And then they end, so we've got 35, 145, 215, and 325. The definition that we're going to learn right now is something called a reference angle. Okay? The definition that's in your textbook is the acute angle that the terminal arm makes with the x-axis. Okay? What I'll get you to write off here, off to the side, as some additional things to help you with the definition. Okay? Your reference angle is always a positive angle between 0 degrees and 90 degrees. Okay? It's always a positive angle between 0 degrees and 90 degrees. Their definition says that by saying, is the acute angle. Okay? But I think this is, wording-wise, helps you remember, okay, it's positive, and helps you remember that it's got to be between 0 and 90. And it's always to the nearest x-axis. Because sometimes you're going to get tempted to make it closest to the y-axis, especially when it gets really close to a y-axis, it gets more tempting. So if you remember, it's always a positive angle between 0 and 90, and it's always to the x-axis. So see that in the second one here with 145 degrees, that 35 degrees is to the nearest x-axis. Here in quadrant 3, do you know the quadrants? Do you remember the quadrants? And how to, this is the first quadrant. This is the second quadrant, the third quadrant, and the fourth quadrant, because it splits it into 4 quarters. Yeah, because it's like thinking of your angles in standard position because they go positive and counterclockwise. We count 1, 2, 3, 4 backwards in that way as well. Mr. LaFrance has a clock in his room that is backwards. It is it is hard to read because you would imagine it starts, 12 is at the top, but then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in the other way, and the hands all move backwards, and your brain just goes, whoa, as you try to figure it out. Yeah. At lunch today, go in and see what time it is. So the nearest x-axis, this is your x-axis here, right? So now here's my terminal arm. It's closest to this x-axis there. We don't go to the y-axis, and we wouldn't go all the way back to that one because that's not the closest. So what I want you to do is I want you to recognize a pattern that happens with sine, cos, and tan. Because what happens in grade 11, whereas in grade 10 you learned sine, cos, and tan just for triangles that were 30 degrees, 45 degrees, it is possible to do sine of 120 degrees. Even though you can't make a triangle with 120 degrees that's a right triangle. Because SOHCAHTOA only works with right angle triangles. You can also do cos of 200 degrees. And that's really hard to make a triangle where one of the angles is 200 degrees and the other two have to add up to 180. Right? Because that just like, whoa, that doesn't quite work. And yet, in certain types of math, we need sine, cos, and tan to work for angles that go bigger than 90. So what I want you to do is take out your calculator and look for a pattern. Okay? For each of these 4 angles, 35, 145, 215, and 325, what I would like you to do is write with a pen, not a highlighter, sine, cos, tan, and then do each of them for 35. That's our quadrant 1. Then in quadrant 2 was 145, So do sine, cos, tan for 145. Quadrant 3, sine, cos, tan of 215 degrees. And finally in quadrant 4, sine, cos, and tan of 325 degrees. Round to 3 decimal places, or 2 decimal places if it looks like you're going to run out of room. We'll do 3 decimal places. 3 decimal places for each of those. Take out your calculator and then look for a pattern. Something special happens. Basically what's happening is for angles that are bigger than 90 that you couldn't make a regular triangle with. See, here's our 35 one. Can you see you can make a nice little triangle there? What they do for 145 degrees is they say, well, my nearest x-axis is there, that's where the triangle would be, and my triangle would be identical to the triangle that I drew in my first quadrant. And if I drew a 35, if I drew it like this, it's the same triangle just flipped down. And if I drew it over here, it's the same triangle just flipped down. Oh. So that's why if you have the same reference angle, sine, cos, and tan will be the same. However, there is a slight change. And if I circle the positive ones, we notice that this one's positive. All of them are positive in quadrant 1. But in quadrant 2, sine was the only positive one. In quadrant 3, tan was the only positive one. And in quadrant 4, cos was the only positive one. So not only are the triangles the same, they start to use positive values and negative values in here. Now let's just look at sine. Sine being the opposite here over the hypotenuse. It includes the y value. If in all of these triangles, this is my hypotenuse here, my hypotenuse there, my hypotenuse there, what they decided is no matter where the hypotenuse is, we're going to say that that length is a positive value. However, when I get to quadrant down here, this one is in quadrant 2. Can you see my opposite is still a positive value for y? So in quadrant 2, sine is still positive. But in quadrant 3, my opposite value now goes down. And what we do when we graph things or when we label things that are going down, we would say this length is negative now because it's going down. And so sine becomes negative in quadrant 3. And can you see that your opposite side goes down there and would be negative as well? What about our adjacent sides? If I went backwards in quadrant 2, adjacent would be negative. So adjacent over hypotenuse, when we go to cos here, we get a negative value. Same thing for tan, because it would be opposite over adjacent. And the opposite is positive and the adjacent is negative, so a tan value becomes negative. In quadrant 3, our adjacent value is still negative, so cos is still negative. But not until quadrant 4 is the adjacent value positive again, so that's why cos is positive in quadrant 4. Why is tan positive in quadrant 3? Because it's a negative and a negative. The opposite side is negative, the adjacent side is negative. Negative divided by negative makes positive. So this is the reasoning behind why the ones we circled are the way that they are. There is something to help you remember it. In English, we call it the cast rule. The only reason it's called the cast rule is because if you draw all 4 quadrants and you say all of them are positive in quadrant 1, in quadrant 2, only sine is positive. In quadrant 3, only tan is positive. And in quadrant 4, cos is positive. So if we did it should really be the Astica rule, but it doesn't quite flow as a word. Astica. because that would be the proper quadrant 1, quadrant 2, quadrant 3, quadrant 4. But it doesn't make a nice English word, so we put the C first and just spell C-A-S-T, cast, as a way to... It just tells you, so the cast rule tells you which trig thing is positive. If you have an angle in quadrant 1, sine, cos, and tan will all be positive. But if you go to quadrant 2 and you have an angle, you know only sine is positive. The other two, because there's an S here, cos and tan will be negative in quadrant 2, which we saw here in our values. If you go to quadrant 3, only tan is going to be positive. Sine and cos are going to be negative values. So this is a quick, helpful way to remember the pattern we saw here, which is based on thinking about our opposite and adjacent sides and where they would be positive and where they would be negative. But we use this little rule to help us find it quickly so we don't have to like redraw our triangles and think it out every single time. So that's the cast rule. Now we're going to do some reference angle questions here on the next page. You just look up at the board. If you have 155 degrees, what would the reference angle be? Not 35, close. 25. There it is. That's the nearest x-axis. It would be 25 degrees. And the reason it would be 25 degrees? Well, the easiest way to figure it out is to say, well, I know all the way to here is 180, right? And if I've got 155 up to there, what adds up to make 180? Or you could do 180 minus 155 to see what would be left. Here we've got 235 degrees. What would the reference angle be? 55 degrees. Again, there it is right here. That's the nearest x-axis. What strategy would you use to figure that one out? Again, I know up to here is 180, right? 180 plus something is going to equal 235. Or I can basically say 235 minus the 180 will be what's left, and that'll be my 55 degrees. Here's quadrant 4, 310 degrees. It'll be 50 degrees, correct? And again, now, a strategy would be, you know, all the way around is 360. So then you could subtract the 310, or say, what would add 360 to get the extra 50? We'll add one more here. We'll do one negative 1. What if I did negative 100 degrees? What would your reference angle be? Oh, and reference angles, we often write theta with a little r to say it's a reference angle. What would the reference angle be here? $80 degrees. Good. Because the nearest x-axis is here. I did this one on purpose because I wanted you to be tempted to say 10 degrees. Because it's only 10 degrees away from this 90, right? So you're like, oh, it's so close. But it would be 80 degrees and positive 80 degrees even though the angle is negative. Because our reference angles are positive angles between 0 and 90 degrees, always. And they're always to the nearest x-axis. So for these questions that were reference angle questions and introducing the cast rule, you can do questions 3, 4, 5, and 7. And I'll give you some time to work on those right now.